Hello, my name is Rob Reynolds. Welcome to Business Calculus Chapter 4, Section 2. Today we're going to learn about natural exponential functions and several formulas and their meanings. The first thing we're going to look at is the integer e, which is approximately 2.71828. And there's more digits, just like there's pi, there's more digits, but that will suffice for now. There's also a function called a logistic function. We're going to look at an application of that. Here's maybe a formula that you remember from your business calculus day. It's compound growth. And then if it's compounded continually, then we'll use this PERT formula. Here, n is being compounded either weekly, monthly, or daily. And if daily, then n is 365. If it's weekly, we'll use 52 weeks and years. Oh, by the way, daily, I think sometimes in business class you use 360. So in math class, we're going to use 365 for n. And this is the effective rate. And of course, the annual rate might be different than the effective rate because of compounding. So if it's being compounded, the actual rate might be a little bit different. So we'll look and explore some of those compound interest, and then we'll look at some present value, which takes this formula and solves it for P. So the first thing we're going to look at here is this natural exponential function. Perhaps you've seen this natural log of x, and that's when you have the natural log base e. It's understood to be base e. If I don't have a natural log and I write log, then it's assumed to be base 10. So what is this e? How does it get generated? Well, if you push x to 0, you'll get this e value, and you can explore that. Just let x get closer and closer to 0. This is the approach, the limit formula. And of course that comes in this formula. You can kind of see it kind of here, and that's why this n disappears, and it's going, and we replace that n rule with e. Actually, if you let n go to a really large number, so this form is a little bit different, but 1 plus r over like 10,000 to the 10,000, I believe is getting closer and closer to replacing this with e. So here they've got it going to 0 for a different reason, and I won't go into all the mathematics of why. There's also something called a natural exponential function, which deals with this logistic growth model. Let's start here with this an example of this logistic growth. An exponential function, of course, looks like this, where you've got a horizontal asymptote at y equals 0. And then in the real world, you're only really kind of just talking about this start value 1 comma or 0 comma 1. But a logistic growth model does something like this S shape. So an example of that would be bacteria growing in a petri dish. You know, it can't grow infinitely because it only has so much space. So it grows exponentially at first, but then the petri dish becomes full and there's a maximum amount. Populations do this as well. There's only so much growth a city can sustain. So after time passes, we're going to let time be 0, time be 1, and time be 10 hours. We're going to find the weight after so much time. And so it's literally as easy as plugging into your calculator. So practicing this, remember I've shown you this trick before. If you hit alpha y equals and then press enter, it'll give you a fraction bar. That will make it easier for you to, so you don't have to use so many parentheses. So 1.25 divided by 1 plus 0.25. E is second ln. This is the fastest way. There's other ways to get e, because that'll give you the caret up as well. Negative 0.4, and then if you just do times 0, of course that goes to a 1, but I'll do this for now. Well, that's how to graph it. Good grief. Let's get out of here. Second quit. Can I try this one more time? Do the same thing. Alpha y equals, I kind of wanted to show you in this form so we can quickly edit this. I apologize. So I'll get out of the graphing mode and type this back in, and you can see that this is close to 1 gram. Now we want to change this 0 to a 1, and you can do that by hitting second enter, which is what I did last time because I typed in a 1.25 instead of a 0.25. But you can quickly edit, so you don't have to retype all this, and just change this to a 1. And then you could hit second enter and then change that to a 10. So let me show you another method. That's one way to do it. If you did type this in over here, instead of typing in a 0 for, oh my goodness grief. Okay, instead of typing in a 0 here, let's just let that be the variable because we want to change that to a 0. So then if you go to second table up and change this to an ask, you can literally just ask what happens at 0, what happens at 1, what happens at 10. And that should give you the same answers. You can see, oh my goodness, I have so many typos. It's like, how are you supposed to learn? Okay, so right here, if you hit second delete, which is an insert, let's change that to a -0.4 instead of a -4. So then if I hit second table, there we go. There's the answers. 1.71 is this one and 1.244, finally, without any typos. Very hard to type in with my calculator. Hopefully you'll have better luck. So there's a couple methods using your graphing calculators. And of course you could graph it as well. Compound interest, we talked about this formula. If you're finding the balance after just 1 year, then time equals 1, and that's why they didn't put anything in there for that formula. So you could go ahead and play around with the compound. We talked about daily being 365. Be careful in business. Sometimes you use 360. But here's all the n variant. And you can see it doesn't change the overall amount, maybe by $3. You would think if somebody's in there figuring your interest every day, opposed to just once a year, you would have more than a $3 rate change. But it's not much difference. This is a little bit about that discussion that I had earlier. As x goes to 0, that really means n is getting really, really, really large. And that's what forms this e value that we talked about. So again, I always think of the musical, I'm going to wash that man right out of my hair. I don't know why, but PERT formula. Sometimes you just refer to this as the PERT formula. But remember, in this example, time was 1. So an example of that would be this. We're going to deposit $1,000 at a rate of 8%. So that you need to identify that that's the P and that's the R. And then you simply punch that in to your calculator to get a value. So that's being compounded continuously is the key word. So we have two different types of compounding. And whenever the keyword says compound continuously, we're going to use that PERT formula. We're going to explore again a little bit of the difference between compounded continuously, which is the PERT, and compounded quarterly. So here we're going to be using the PERT formula, compound continuously, or that E. And if it's compounded quarterly, then we're going to let n equal, well, it looks like we're going to do that for both the 7% and the 11%. Let's start with the 7%. If it's compounded quarterly, we're going to let the n be 4. Because there's 4 quarters in a year. And it looks like time is going to be for his 25th birthday. So it looks like time is going to be 25. And the P, we're going to deposit $12,000. So why don't you pause the video. If you haven't already, go to Blackboard, print off the worksheet that I have there available for you, and see if you can't get some answers to plug in for that. So in part A, if you've worked it out already, 12,000 e to the 0.07. It's important for you to try to type these in before I give answers, because sometimes people have this on their worked out solutions, but then they have wrong answers, and that's just always really painful. In part B, it's similar. You're going to do 12,000 1 plus the rate 0.07 divided by 4 raised to the 4 times 25. So see if you can't get both of those answers and compare them at the 7% rate. So it's around 69,000 and then 68,000. So that's not much difference. Again, 68, 69,000. Well, over 25 years, that's more than what we had before. Now, 11%, look what happens. That's a big jump between 68,000 and, well, I'll compare the 80,000. That's a big jump, because you wouldn't think it would move that much from 7% to 11%. But again, because of so many years has passed, that's significant. So the lesson there is start investing early. So here's the graph of the two, and you can see that you'd probably choose part C because, well, the effective rate for being compounded continuously at 11% is really effective. And so that's what we're going to talk about, this effective rate. And so the actual rate that you're getting is a lot more than just 11% because it's being compounded. And the compound produces a lot larger. The nominal is the same thing as the annual. So your annual percentage rate is 11%, but because of compounding, it's a heck of a lot more than 11%. And so to figure effective rate, we use this formula. And here's an example. Let's try to plug in 6%. So it's going to be 1 plus 0.06 divided by 1, because we're going to do it annually at first, raised to the 1 minus 1, and then 1 plus 0.06 over 2 raised to the 2 minus 1. And again, I really think the easiest way is to do this is let whatever's changing from well, first you let it be a 1, then you let it semi-annually 2, then a 4, and then a 12. So I would just go to your y equals. And instead of letting n be 1 or 2 or 4, just let n be x in your calculator. And then if you go under second table, I'll just type right over the answers that I had before. I want to check a 1, 2, 10, no, 4 for 4 for compounded quarterly, and then compounded monthly is a 12. And what you're looking over here are percentages. So this is 6%. This is 6.09%, 6.14%, and 6.17% is the actual effective rate. And so here it's worked out by hand, but there you can see the effective rate was at 16, 14, and 16, 17. Some present value means we're going to be solving the formula for P. This formula works well if you know that you're going to be having a kid that needs some money in college, in 18 years, and you want to know how much should I invest now so I can end up with, did I say 30? How about 80,000 or 180,000 depending on the college that he goes to. So sometimes we know this amount, the total that we have to have after so much time. So how much should I invest now in order to get there? So we kind of play around with the formula a little bit, and we just solve that for P. Either you can memorize this or you could just use the same formula and just algebraically solve for it. Sometimes they replace that R over N with just an I, which just means that's your interest rate per compounding period. And then instead of raising it to the NT, they just change that to a capital N, standing for the total number of compounding periods. So you can use whatever formula you so choose. For this example, I'm just going to continue using the same formula. Solved for P, 1 over R over N raised to the NT. And I'll start identifying. Looks like I've got 15,000 here. You should pause the video and see if you can identify these. 0.08, 12, and 10. Remember, mathematics doesn't work well if you just watch me work problems. You really should be working them out yourself. So plug those in for P, and again, I highly recommend, even if you can plug this in successfully, that you should take out your own calculator and see if you can't type this in correctly. It's amazing to me how many people can get to step A, but they can't get the correct answer. So you need to actually practice the skill on your calculator. So pause the video, type this in, and see if you get something around 6,000. Hopefully you got 6,757 and 85 cents, rounding to the nearest penny. I don't know if that happened or not. There it is. The last part is just some more examples that I would highly recommend that you kind of work through. These are problems just straight out of your book. And trying to identify which formula to use is probably the most important thing. So I'll just start you out. I see compounded continuously, so I've used the PERT formula here. Here's the worked out solutions. Try that. This one says the effective rate. So this might be a good test where I give you a formula sheet, because I don't expect you to have all these memorized, but you'll probably have these memorized by the time you work several of these off of your WebAssign homework. So there's the formula for effective rate, and there's the worked out solutions. This one's talking about compound and how much should you deposit, so kind of like that last formula that we just looked at for the college, how much money should I have after so much college. And all they literally did was took this, and sometimes students don't want to memorize this formula here. We'll call that formula B. Sometimes they just keep plugging it in right here, and they just plug in for A, plug in for all of this, and solve this for P instead of memorizing a new formula. So if you just memorize this one, you don't really need, we'll call this equation formula A. If you know equation A, you don't really need equation B, but no, B is a little bit easier. If you have a cheat sheet, we should probably just put it on there. There's the worked out solution for 38. And 39 is future values, so you really are going to be using P, let's write the formula correctly. A is equal to P1 plus R over N to the NT. So practice going through and reading problems and figuring out which formula to use for this. But even more importantly, practice plugging these in and actually typing these problems out. Here's worked out solutions. I hope this video was helpful. Email me with your questions. Thanks.